This is lesson 3.2, and today we're going to be learning about energy level diagrams. So our goal is to learn how electrons are organized in atomic orbitals, and that organization is called energy level diagrams. Let's start off by just looking at an energy level diagram and try to make some sense of it. All right, this is the hydrogen energy level diagram, and what is everything here? First of all, a single box is one atomic orbital. Next, a group of boxes is a subshell. So what do I mean by group of boxes? So up here, you'll see a group of boxes. This is one subshell, and they're a group because they're one single subshell. Notice that this 2p subshell right here, this is telling you which subshell it is. This 2p subshell has 3 boxes in it, and we expect it to have 3 boxes because we remember that for every p subshell, it contains 3 atomic orbitals. Next, what is this thing right down here? It might look like the number 1, but it's actually a half arrow. Each half arrow represents an electron. Now, you could possibly draw a full arrow if you wanted to, but chemists typically draw half arrows simply because they can draw them faster and easier. So a half arrow like that or like that, each half arrow is going to represent an electron. And we're going to talk about why they're up or down here in a minute. Now, I want you all to remember that just like bowling balls on a hill, electrons all want to go down to the lowest possible energy level. And we remember that the lowest possible energy level is the 1s energy level, or the 1s atomic orbital, okay? Now, of course, they can't all go there, right? There is a limited number of space. So just like people need space, electrons need their own space too. So we can see here on this sofa, you can fit 2 kids, all right? It's going to be the same for your electrons, right? There's a limited number of electrons that can fit into one atomic orbital. And it turns out that at most 2 electrons can occupy one atomic orbital. In addition to that, those 2 electrons must have opposite electron spin. So one's going to be spin up and one's going to be spin down. This is known as the Pauli exclusion principle. Now, you might be wondering, what in the world is this spin up, spin down thing? It turns out that electrons are all magnetic. So an electron appears to be spinning. Whether it's actually spinning or not, we're not sure. But the electron appears to be spinning, and that's going to give it a magnetic polarity. And so, for example, if this electron were spinning this way, you'd have north up and south down. And if it was spinning the opposite way, you'd have north down and south up. And so by spin up and spin down, we're referring to that magnetic polarity of the electrons. And so if you have 2 electrons in one atomic orbital, one of them is going to be spin up and one of them is going to be spin down. They have to have opposite magnetic spin. And in that case, their magnetic poles are going to cancel each other out. So back to the hydrogen energy level diagram. Now we notice that the hydrogen energy level diagram has only 1 electron in it, right? This half arrow represents an electron. And that makes sense because hydrogen has only 1 electron. So what happens when you get more and more electrons? Well, we're going to fill in these boxes. So once again, let's remember what everything is. This box down here at the bottom is the 1s orbital, and it's lowest in energy. And we represent that by drawing it down here at the bottom. After that is the 2s orbital, which is higher in energy, so we write it above the 1s orbital. After that is the 2p, which is also higher in energy than the 2s, so we write it higher. Now remember that the 2p subshell has 3 different atomic orbitals because every p subshell has 3 atomic orbitals in it. S subshells have only 1, and remember the d subshells have 5. So when we come around to writing the 3d subshell, we're going to go ahead and put 5 boxes in it. Now we want to put these electrons in the lowest possible energy level. So of course, that 1 electron for the hydrogen is going to be in the 1s subshell, or the 1s orbital. And as we get to atoms with more and more electrons in them, all those electrons are want to go down as far as possible. They're all going to want to get into the 1s. But of course, we can only put 2 electrons in each box. So after hydrogen is helium, right? Hydrogen has 1 electron, helium has 2 electrons, and feel free to follow along with me on the periodic table. And we are going to put both of the electrons where? Of course, we're going to put them both down in the 1s subshell because you can fit as much as 2 electrons in one box. And so we see for helium, we see 2 electrons down in that 1s subshell. Notice that those 2 electrons are opposite in spin. One is spin up and the other one is spin down. That's very, very important, okay? You cannot possibly write them both up or both down. They have to be one up and one down. Now, after helium is lithium, and for lithium, we have 3 electrons, and those 3 electrons cannot all fit in the 1s subshell, so we need to put one of them up in the 2s subshell, so it's going to look like this. Now, typically, I write the electrons up before I write them down. There's no real rule telling you have to do that. You could make this a down arrow first, but it's nice to follow a rule to always do this in a certain way. So I always start off by writing the arrow up. After lithium is beryllium. Beryllium has 4 electrons, and so that 4th electron is going to go where? That's right. It's going to go in the 2s subshell. And we're going to put it down because if you have one up, the other one must go down, right? They cannot both be pointing the same direction. After beryllium is boron. Boron has a 5th electron, and it is going to go where? That's right. It's going to go up into the 2p subshell. Now, again, it doesn't matter which of these boxes that you put this first electron in. It could be in this one, or this one, but it's nice to have a way to always do these energy level diagrams. So I'm going to always put that first electron in the first orbital right here. Then, as we put more and more electrons into these atoms, you can put them into the other boxes. Now, after boron comes carbon, and carbon has 6 electrons. Now, that 6th electron has some choices. Where's it going to go? Is it going to be paired up with this electron, or is it going to go in one of these other boxes? It turns out that carbon is going to put its 6th electron right there. We could have also put it over here, but once again, I like to write them from left to right rather than skipping any boxes. But you are not going to put this electron paired up with this other electron. Well, why is that? It turns out that those electrons all want to have as much space as possible. They don't want to get close to each other. Well, why? Because each electron is negatively charged, so they want to get away from each other. Remember, 2 negative things are going to repel each other. So as long as those electrons have the same energy, they're going to want to get as far away from each other as possible. Remember that in the 2p subshell, all 3 of those orbitals has exactly the same energy. So in order for them to get as far away from each other as possible, they are not going to pair up. In general, if more than one atomic orbital of the same energy is available to an electron, electrons will go in different boxes. That is, they will occupy different atomic orbitals, and they will have the same spin. This is known as Hund's rule. So not only are we going to put this other electron in a different box or a different atomic orbital, but it must be pointing the same direction. So if this is spin up, this one also must be spin up. And our third one must also be spin up. You cannot write one up and one down. They cannot have opposite spin. And the reason for that is they don't even want the possibility of being able to pair up. They will sense that somehow, and that will cause them to be unhappy. So you want to make sure that you have all of these electrons having the exact same spin. So they're all spin up or all spin down. I'm always going to make them spin up first. It's nice to do the same thing every single time. Now, after carbon, we have nitrogen, and we've already said that that other electron is going to go up into the 2p subshell in another orbital, and it must be pointing up because of Hund's rule. After nitrogen is oxygen. Where is that last electron going to go? That 8th electron. And at this point in time, it must pair up with something. So it's going to pair up with the first one there. And here is the energy level diagram of oxygen. Now we're going to follow these same principles for doing all of the different energy level diagrams that we draw. You may have also noticed that all of these boxes are always the same for all of the different elements. And that's going to be the case for all of the energy level diagrams that we do. The only thing that's different is the electrons, the number of electrons in each one. The way that they fill is going to be the same. The only thing different for each of the different elements is the number of electrons, and that's it. All right, let's try to do a couple sample problems here, and I'm going to go ahead and start with the energy level diagram of oxygen. All right, so if we're going to do the energy level diagram of oxygen, the first thing that you're going to want to do is to look up on the periodic table to make sure that you know how many protons and electrons it has. So oxygen is element number 8. You can find it right here. And so if it's element number 8, you know that it has 8 electrons. So go ahead and write that down, 8 electrons. And once you know that, you can go ahead and write your boxes in. So for all of these, the bottom box is going to be your 1s orbital. And then after that is going to be the 2s. And then after that is going to be the 2p. That order is never going to change. It's going to be the same for all of these. Now, I'd like to comment here for a second that make sure you do your boxes the same way that I did. There's a reason behind this. First of all, make sure that you have space here between this, okay? So there should be space between your 1s and 2s orbitals. They should not be connected. So if you're writing them like this, so if you have them like this, if you're drawing them with them all connected, that's not correct, okay? So make sure you don't do any kind of drawing like that. And the reason for that is that this space tells us that these are different energy levels. They have different energies. So electrons in this energy level are not the same. They don't have the same energy as electrons in this energy level. So these are energy levels. Yes, they're subshells, but they're also energy levels, and they have different energies associated with them, so there should be space between them. One other thing to note, where should there not be space? There should not be space in between these. So when you draw, for example, the 2p subshell, right? So that 2p subshell, make sure you're not drawing it like this. So if we have, so here's your 1s, your 2s, and make sure you're not drawing something like this, all with separate boxes. Well, why is that? Why do you want to put all three of those boxes together? And the reason for that is that these boxes are all in exactly the same subshell and have exactly the same energy. So we want to connect them together to show that they're the same subshell with exactly the same energy. All right? So please don't draw them as separate boxes like that either. Okay? Make sure you draw your boxes like this and label them, and then you can go ahead and put the electrons in. All right, so once we know that these boxes are going to be the same every time, and please draw them in this fashion, then we can go ahead and put the electrons in. We have 8 electrons. We're going to always start from the bottom, and when we put them in, we're going to put 1 up and then 1 down, so that's 2, 3, 4, and then once you get up to here, make sure that you put your electrons in all the same direction first. So that's going to be 5, 6, 7, all the same direction, all pointing up before you ever put another one pointing down. And so the last one we're going to put right there. All right, I'm always going to put them up first, and I'm always going to go left to right. There's not a real reason. They can be pointing down, all pointing down, and then one pointing up. That's also okay, but I'm going to always start with them all pointing up first. All right. All right, we're going to try one more sample problem today, and it's going to be a little bit of a more challenging one. Let's go ahead and write out the energy level diagram of chromium. And so like before, the first thing that we want to do is find chromium on the periodic table. All right, and so on the periodic table, we find chromium in the middle here. There it is, element number 24. It is one of the transition metals, so element number 24. That means that chromium has 24 protons and 24 electrons. So go ahead and write that down, 24 electrons. And then next, we're going to need to know exactly which boxes to draw. So it's going to be a little bit more challenging for chromium because there needs to be enough boxes for 24 electrons. So we're going to use one technique called the diagonal rule to figure out the order of all of the different boxes that we use. All right, and this diagonal rule is going to work for any of the elements. Yeah, there are a few exceptions, but for the most part, we're not going to worry about any of the exceptions. The exceptions are not important. We're instead going to look at this diagonal rule, and it's going to work for us for all of the different elements. To do the diagonal rule, we're going to start off down here at the bottom, and we're just going to write in 1s, 2s, 3s, 4s, 5s, and we could continue on here. I'm not going to get all the way up to the 6s or anything like that, okay? But we write in here, have a column of s's. And then after that, we recognize that every time you go up in principal quantum number, you gain an additional subshell. So the 1 has only the 1s, the 2 has a 2s and the 2p, the 3 has a 3s, the 3p, and the 3d, the 4 has the 4s, the 4p, the 4d, and the 4f, and the 5 has the 5s, the 5p, the 5d, the 5f, the 5g, and of course we're not going to ever get to the g or anything like that, okay? So it's kind of too much information there. We don't need all of that, all right? But let's go ahead and use this. To figure out the order of these boxes, we're always going to look up and to the left. So our first box, and we already knew this, our first box is the 1s. I'm going to go ahead and draw the 1s box down here. All right, after that, again, we already know the order of the initial ones, but let me draw it here anyway. Our next thing that we're going to fill up is the 2s. And so again, the 2s, we know that is simply a single box here, 2s. All right, after that, we're going to come to our next diagonal, and the first thing in the next diagonal we find is the 2p. We already knew this. The 2p, because it's a p, should have 3 boxes in it. Remember, all your s's are going to be 1 box, your p's are going to be 3 boxes, our d's are going to be 5 boxes, f's are going to be 7 boxes, and we're never even going to get to the f's, let alone the g's. So anyway, so we have the 2p. After the 2p comes, well, just let's continue and follow this diagonal up. So we have 2p, and then we have the 3s. And the 3s, we know, is simply just 1 box. After the 3s, we're going to try the next diagonal, and it's going to be the 3p. Again, always follow these diagonals up and to the left. So the 3p should have how many boxes? Yep, that's right, 3 boxes because it's a p. After the 3p is what? The 3p should be the 4s. So we're going to go ahead and write the 4s right here. 4s has only 1 box because it's an s. Now this might seem a little bit strange at first, but it turns out that the 4s is actually lower in energy and comes first before the 3d. So notice the 3d comes here on the next diagonal. All right, and the reason for that is simply the 3D has so many of those twists and turns in it, and that its energy is actually a little bit higher than the 4S, even though the 3D is smaller because it's only n equals 3, whereas the 4S is n equals 4, and so it is bigger. Okay, now those two energy levels, the 4S and the 3D, are actually fairly close in energy. And so that's where some of our exceptions are going to be. Sometimes the 4S is higher, sometimes the 4S is lower. But for our purposes, we're always going to draw the 4S before the 3D. And we're always going to follow the diagonal rule. All right, after the 4S, we have the 3D. And that 3D is going to be how many boxes? That's right, 5 boxes. Remember, all D subshells are always 5 boxes. And I'm going to draw my D subshell like this. I'm going to draw it as a nice long rectangle. And then what I'm going to do is I'm going to take out that middle box and then cut each of these in half. And that seems to work pretty well. So that's going to be my 3D. And then after the 3D, we're probably not going to need that for chromium, but let's go ahead and do it. After the 3D is the 4P. And the 4P, once again, is going to be 3 boxes right up here. 4P. And then after that, you can continue on and see, well, after that should be the 5S. After the 5S is going to be the 4D. After the 4D is the 5P. After the 5P is the 6S. After the 6S is going to be the 4F. And that's going to continue on and on like that. Okay, so this diagonal rule is universal for all of the elements. All right, the order for these boxes is going to be the same for all of the elements. So this is pretty powerful. Again, it's going to tell you the order of the boxes, and it's also going to help you have a visual way to figure out, okay, which orbitals don't exist and which orbitals do exist. So these that I've drawn are all the different orbitals or subshells that do exist. All right, now let's go ahead and fill in the boxes here. Let's put in the electrons in the appropriate places. We have 24 electrons, and the way you fill this is important. So we're going to start off down the bottom, and I'm going to start off with 1, 2, 3, 4, 5, 6, 7. Always going to half fill these orbitals before you pair anything up. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Make sure that you pair this up before going to a higher energy level. Remember, the electrons all want to get to the lowest possible energy level, and after that, they want to have as much space as possible. All right, so we have 20 electrons in there so far, so that means we need 4 more. That's going to be 21, 22, 23, 24. All right, that is it for chromium. Make sure you follow my example when you're doing the energy level diagrams for other elements. You're not going to get anything beyond this, and you don't need to. So I didn't need to actually draw in the 4P because it's completely empty. But if you have an empty energy level or an empty subshell up there, not a big deal. Okay, make sure you do always draw complete subshells. So this box here, this empty box here at the end of the 3D is important. You need to make sure you have that empty box because it shows that you know that the 3D has 5 boxes in it because there are 5 orbitals for the 3D subshell. All right, so we're going to go ahead and end there. Stay curious. Keep on working on these energy level diagrams. The more you do, the more you know. See ya.